Welcome again to another episode of the Sustainability Podcast. Today I'm very excited to be joined by Marc Borrett, founder and CEO of Reactive Technologies. Welcome, Marc. How are you today?
I'm very well, Jim, and pleasure to be invited to join you and your listeners today. Thank you.
Great. Can you tell us perhaps a little bit, just to get started, a little bit about yourself and how you came to this ecosystem?
Yes. Well, my journey was an unconventional one, I guess. I actually started out working in the world of semiconductors and was lucky enough to be involved in a UK company that I also co-founded that pioneered near-field communication. So if you use your phone as a contactless payment device, then that most likely has got our chip IP in it. We licensed it to most of the world's largest chip makers. And then that business was sold to Broadcom in 2010. It was a public company. And at that time in 2010, I was very interested in a new challenge. And the energy industry appealed. There was a lot starting to happen. And I saw that there could be an opportunity to bring a different set of skills to some of the challenges that the energy sector was facing and is still facing today, and really bringing the skills from the world of mobile communications, looking at things in greater detail, understanding signals in amongst a lot of noise. That seemed to be missing, and it's obviously a huge part of telecommunications and a huge part of chips. And so that seemed like a very interesting entry point to come into a new industry from a different perspective. It seems to have served a purpose. So we co-founded Reactive in 2010. We filed some initial patents around how we could control devices right at the edge of a power grid. And so our focus was actually demand response. That was quite similar to telecoms. Telecoms have gone on a very similar journey. They've gone from fixed line, routing a call from one caller to another through a series of physical exchanges in a quite linear way, and to move to effectively voice over IP. And the energy sector seemed like it was going to go on a very similar journey, albeit in a very different way, from quite a linear power grid with a few big generators producing high voltage electricity, and then in a linear way bringing that down and down into homes and businesses with lower and lower, safer voltages. And yet the grid was changing. It was going to have to deal with rooftop solar, with EVs, and so you could see, or we could see, some interesting parallels, and maybe the world of mobile communications might offer up some interesting different approaches to take, and that's how we got here.
That's fascinating. So you saw more of a master-slave network that was evolving into more peer-to-peer and certainly more connectivity.
Yeah, I think that's probably a better way of describing it than the way I did. But from an engineering perspective, what was interesting is we recruited, coming from the semiconductor world, we recruited a number of engineers from Nokia. So what was interesting for those engineers is that they had to think suddenly very similarly, but also very differently. So, in a mobile phone, power consumption is critical. So, you want to reduce the power level down to millihertz. In the power grid, we want to talk about milliwatts and megawatts. And when you talk about sort of frequency of signals, then you're in the domain in the mobile world, mobile communications world of millihertz. And equally, when we were looking at data rates, then, we were thinking more about megahertz. So there were some interesting areas which made the team have to think differently and understand the power grid not as a power grid, but as a communications channel. And how could data, or how could we interrogate that whole power system with different tools that have been available, up until now. So it was also very exciting for, very high end, well qualified, innovative mobile communication engineers to suddenly be presented with a whole new set of challenges, but using the tools that they'd used and known very well but applying them in a very different way.
That's interesting. I mean, a number of questions come to mind that certainly coming from the mobile communications world and having that critical eye on energy truly conservation, it brings up the idea that so many devices on the grid today are what's informally called power vampires.
Yeah. Yeah.
All the different wall warts and everything, all of those. So what insights did you and your team develop because of your unique perspective coming from the mobile communications world?
So we had some interesting conversations with some grid operators to start with. So, having a technical team who really just want to sort of start to explore the power system, we had some conversations initially around, well, there's a lot of assets that are not actively used in the way they could be used to help with this energy transition, to suddenly be able to be brought into use to manage more and more surplus power. So the first area we looked at was immersion heaters, hot water heaters in the home, where you just have a resistive element in a storage tank, and that heats water up. And certainly from a European perspective, there was a disconnect because, most people leave their houses during the day. Maybe it's changed a little bit now post-COVID, but most people left their houses during the day. 12 o'clock, 1 o'clock was peak solar, and there was very little energy consumption happening in residential homes that would coincide with that sudden peak surge of solar. So our approach to grid operators initially was, well, look, if we had a way that we could send a signal through the power system that could instruct an immersion heater to switch on at a particular time in a particular region of the country, would that be of interest? And the resounding response was absolutely it would be. But they said, how would we do it? It's incredibly difficult to, cover that last mile. Some of these immersion heaters are in basements, they're in garages, Wi-Fi may not work. So that they saw that as a challenge. And our approach was, well, what if we could, actually send a signal through the entire power grid that could be received at any single point on that power grid, and then it would contain in that signal a code that would give an instruction to a particular region to actually switch on rather than being in an off state, consume that additional surplus solar energy, heat water, rather than just, letting it go to waste. So we set up a project. And it was, we very much felt like, we were talking black magic, to the grid operators, because it was still quite fanciful what we were talking about. And effectively what we did was we had some assets. These were, load banks, so huge resistors, relatively speaking. And we would, switch them on and off in a particular sequence that would create a code. We had them this is all in the UK, in about, just over 10 years ago. And that switching on and off pattern, because we were changing the frequency of the whole system in a tiny, tiny way with each, on signal or off signal, we were actually changing the power imbalance of the grid, again, in a minute way. So the grid operator simply couldn't see this, but we could see it because we knew where to look for in the noise of the power system. And because it was a code hidden in the frequency, which goes everywhere through every transformer in the entirety of the power system, it would come out at every single socket, wherever that socket was connected onto that power system. And so we performed that. We sent a signal that was called UK OK, so four characters, not obviously a huge amount of data, but we proved that it carried through the entire power system. We had receiver devices in the very north of the country at every sort of compass point, and it went through the entire power grid. And that was, for us, a world first. Working with National Grid, they saw it as a world first. But we realized it wasn't quite the prize that we could go after, which was the interesting next step in that.
Well, Mark, before that is fascinating. But a couple of questions have come to mind for me. Well, first a comment that usually we think of load shedding and not enabling a load during a period of time.
Yes.
So that's interesting about perhaps overdriving the water heater during the day when the power is most available. The second is, I believe I heard that you use power line communications, of course. Have you developed that protocol and that technology, or is that because I know, many entities over the years have tried power line communications for utilities from Echelon and Domosys and Arion and so many others. Can you talk about that before we get into the nuts and bolts of UK OK?
Yeah, of course, Jim. So you're right. So load shedding is I think, is probably the least worst, byproduct of trying to run a power system with more and more renewables. You're wasting clean green power, and so really the objective was, which is still our core mission today as a company. How can we maximize the use of renewable power on the power system, and load shedding or curtailment. Sometimes load shedding is done for different reasons as well. It's actually to stabilize the power grid from a sudden shock, loss of a big generator, for example. But really the initial objective was, well, how can we maximize the use of that renewable energy, rather than it just be wasted. So that was the premise, and that premise as continued today as our key mission. In terms of the technology, we have evolved it, and perhaps we'll go on to how we've done that. But it was different to what people would conventionally think about effectively like power line communication. So power line communication relies on sending a lot of data, actually. So you typically have a high frequency signal injected on top of the 50 or 60 hertz system frequency or carrier frequency. The problem with that technology is when you get in front of, or you get your signal to one side of a transformer's got an air gap in it. And so you're not going to get your high frequency signal to cross that air gap. The core power system frequency does. It goes through the windings or the tap changes. So either the 50 hertz or the 60 hertz frequency goes through, but then you're stuck with how do you get your high frequency where you've got the data, and there you need repeaters. So it becomes a very capital expensive approach, because you've got to put a repeater on either side of every transformer that's in the power system. We didn't do that, or didn't need to do that, because we were encoding our data in the core system frequency, in the 50 or 60 hertz. The positive of that is we went through every transformer in the power system. So we get that full coverage. We don't need any of that additional hardware. those repeaters either side of transformers. The downside is you don't get the same amount of data. You just get a small amount of data. But for the use case of an immersion heater, you don't need a lot of data. You just need to say, switch on for this long if you're in this area. And that's basically, you can reduce that down to a very small and efficient code that you can embed within that core frequency. But that isn't where we ended up going with the technology. We ended up going down a slightly different path, which we felt had actually more merit to actually how you tackle the challenge of actually running a power grid on higher and higher amounts of renewables, but maintaining the system security, keeping the lights on, and still doing that at an economic cost.
That's fascinating, because you probably sensed my concern that power line communications required an awful lot of capital costs, or at least in the legacy world it did.
Yeah.
But this is fascinating. So then, how did you start collecting this data about the health of the network?
Well, it was, I think, like all good innovative breakthroughs, sometimes you don't know what you've developed until you've seen a problem. And the problem that we initially saw was when we sent that signal through the grid, UK, OK, we had receivers that we'd installed around the UK, the country, and being engineers, we know how fast an electron travels at the speed of light, and we know how small the UK is. And when our engineering team looked at the data, they found that some of the receivers took longer to get the signal through to them, or the signal had to be repeated a few times for it to then be properly received by the receiver. So we're talking, tiny amounts of difference in time, but it still didn't follow in every case the same pattern of communication, because where we had cited the generation of that signal to be relatively central, we would have expected all the receivers to have got the signal at pretty much all at the same time, but we didn't, and that bothered our engineering team. And so we really thought about why did that happen, and it was as if something was stopping something in the power grid. A phenomena within the power grid was actually inhibiting our signal getting to our receiver devices. So we looked into it more and more, and we came across this phenomena of power grids called inertia. And the more we looked into this phenomena of inertia, which basically is the quality of a power system that stops the frequency from moving too much. So if you suddenly lose a power station, if you have a high inertia power grid, the frequency will drop, but it won't drop by that much, and it won't happen that quickly to drop. Conversely, if you have a low inertia system and you lose a power station, the frequency can fall very fast. And it can fall at such a rate that you could risk a blackout. And when we looked at our data, we started to see that in areas where there were big conventional fossil generators, our signal didn't get through as easily as areas where there were high amounts of renewables installed. And what that led us to understand is that this phenomena was actually stopping our signal getting through. And then we realized, oh, hang on. If we change the whole system around and put it on its head, maybe we can measure inertia of the power grid. And we discussed this with National Grid in the UK, and they said, that's impossible. You can't measure inertia. We can only see it when a power station fails, and we only see that 6 or 8 times a year. So we don't think you can measure it, and you certainly can't measure it with such a tiny little signal that you're using to sort of change the frequency. So they set us this challenge where they said, well, okay, we'll fund you to measure it, but we're not going to tell you anything about the inertia on the grid. You take the measurements you think you can take, and you give us the answers, and we will mark your homework, and we'll tell you if you're close or not. So that meant that we completely turned it on its head, and instead of putting a code in the frequency, we were then actually sending a pulse of power into the grid, and we were starting to see, by having these receiver devices still in place around the UK, where there were stronger areas of system stability and weaker ones. And then we were aggregating those measurements up into a single measurement that we said was the inertia of the UK grid. And the interesting part for the grid operator was, if this does work, this is now a tool they can use to actually measure in real time how stable the grid is, which suddenly helps them understand operationally how they can maximize the amount of renewables without starting to put the grid into a potential risky situation where, if they did, heaven forbid, lose a big power station, they would still have enough stored energy in the grid from this inertial characteristic to give them enough time to bring on load shedding or fire up batteries, whatever it is that they determine is going to be the right solution to correct for that problem. So we did a second project, and we provided the results. And I would say, luckily for us, a big power station also fell over right in the middle of our measurement campaign, because we were measuring this phenomena, and the grid operator had only been able to estimate it. And there was a difference between what they were estimating and what we were measuring. And it was quite a big difference, actually. In some cases, we were measuring up to 30% more stability than the grid operator was estimating. And in some cases, we were measuring less stability than the grid operator was estimating, which meant that they could see two scenarios. One is, for most of the time, there's actually more stability on the grid than they are able to estimate, which means they could automatically run more renewables more safely, which is a real positive. But then there is also a period of time, roughly 20% of the time, where they are overestimating the amount of stability on the grid. And if they are doing that and they were to suffer a large power station failure, that might put them in a very difficult system risk scenario. And from our measurement data, because of this risk, I said it was lucky that we had a power station fail, because that gave an independent data point. And what that data point showed was that their estimate was 30% away from where the power station failure gave them the figure of inertia, and the power station failure figure was right on the button on our measurement of inertia. And that basically, I think, convinced them that, hang on a second, these guys can measure inertia in real time.
That's absolutely fascinating. I have a question that, in your earlier comment, you talked about propagation of that UK OK signal, and that there was inertial impacts from the fossil fuel stations, but not from but less so in areas that had more renewables. But later on, you talked about it sounded to me like it was one inertial number for the entire grid. Do you develop an inertial attribute for the entire grid, or for segments of the grid, or is it different at many points of the grid?
Yeah, I mean, so this is just going back to the start, bringing this different skill set from mobile communications into the energy sector has helped us and the grid operators we work for understand the power system differently. So when we first started, going back to that first UK OK, we realized also that the frequency of the power system is different in different parts of a power system. The conventional understanding up until that point was no, electricity travels at the speed of light and the frequency is the same wherever you are on the power system. Not true. Not true, because we developed a highly accurate receiver device that could tell us that wasn't true. We had empirical data to show, look, even in a power grid that's, only 800 miles long, we can instantaneously measure a different frequency level down in the south versus one in the north. And because we were capturing this measurement data in much higher precision than the kind of measurement devices that the grid operators have been using, we were able to prove that. So that was the first step. And then, as you've correctly pointed out, Jim, we started to see that also from an inertial perspective. And we see that grids need all different forms. They need a national view, which gives them something in the control room to start to make those operational decisions between, do we run more renewables or do we curtail those renewables because we're getting to an operational limit and we actually need more stability that comes from the conventional generation, right down to regional perspectives. How do we secure new levels or new forms of inertia in this particular region because we can see that it's weaker than these other ones? So do we invest in synchronous condensers, or do we have a specific inertia market that's going to pay a premium for assets that can give inertia because they're located in a particular weaker part of our grid? And we're seeing all of that start to play out now. So the thing I should maybe just share with your listeners is that not all electrons are created equally. And by that, I mean, if you compare an electron that's produced from a fossil fuel-based power generator to a solar or a wind farm, they are different from this inertia perspective. So when you produce an electron from a coal-fired power station, you burn the coal to heat the water, to produce steam, to then use that steam to spin these turbines that spin in the US, let's say at 60 times per second. So you have a 60 hertz power system. And those turbines spin within the electromagnetic field that then produces the high voltage electricity. Each of those turbines in each of those big power stations are synchronously connected to one another. So they spin at the same speed at the same time. So suddenly, if one power station develops a technical fault and suddenly all of that generation power is suddenly lost, you can speed up, or rather those turbines automatically speed up so that they stabilize the power system from that sudden shock. If you then contrast that method of producing an electron to a wind farm or a solar farm, those are DC connected to the power grid. And they only change their production's output based on what's happening to the weather. Is it windier or is it sunnier? Yes or no. So it doesn't matter what's actually happened to the power system itself. They will not change their output other than if the weather changes. So when you bring this renewable transition into the control room in a grid operator, you're dealing with a very, very different grid. So when you had a power system that was predominantly based on fossil generation, that was like operating a steam engine. It was big, heavy. You just had to keep on filling it with coal, and it would just stick on those tracks, those iron tracks, and it would barely move, and it would run through anything. So you had a very, very stable grid, and because you had a very, very stable grid, you didn't really have to measure it, and you could use models to determine how it would behave if certain things changed. And you had plenty of time to deal with problems because it was so big and heavy and stable. But as you have more renewables on there that are basically, inverter based, and you displace those big, heavy fossil generation assets, your power grid doesn't behave like a steam engine anymore. It starts to behave a little bit more like a motorbike. You could stall it. You could fall off of it. So because you have less of that stabilizing capability and you have more of this on, off, generation that isn't doing anything to stabilize your grid, you start to feel in the control room that you're now having to control something that is less stable and you have less time to deal with the problem when it comes along, which means that you need to start to look at your operational margin, and that operational margin becomes how much inertia you've got on your grid, because that's the characteristic that actually determines how much time you've got to solve a problem when it hits. When a power station goes down, it's the amount of inertia or stored energy in all of those rotational turbines that buys you time, that stops the frequency falling completely vertically, and it's that inertia storage factor of the grid that allows you to do load shedding or get batteries to respond or whatever it is you're going to use. So inertia starts to become a critical new constraint that grids have to manage on a real-time basis. Never had to 10, 15 years ago because the grid was like a big steam engine. Now it becomes more like a motorbike, and in some cases, in a direction of travel towards a bicycle, you have to know it. You have to keep it balanced. And it's the inertia in the grid that is the thing that helps you do that.
Those details are fascinating, and that's just tremendous insights and research. Earlier I led with master slave as an analogy describing the legacy power distribution system. I often think of what's coming as a peer-to-peer network similar to the internet, for that matter, where things get routed, of course, down the least the path with least friction. Let's say. So this is fascinating. So, I think you've answered it in a number of different ways, but so what challenges do we have, in moving towards a world where we're, ultimately the majority of our power or all of our power is renewable? What are those challenges, and what solutions are there to get us there?
Yeah. The answer is why I'm also grateful for your kind invitation to do this podcast, Jim, because the objective is how do we transition to renewables, and unfortunately the media pick on the things that are most easiest to explain. So I break down the transition to a fully renewable power system in three distinct areas. So the first is you got to build more renewables. So we had COP28 last year that said, triple the amount of capacity of renewable generation between now and 2030. Great. You got to build those renewables, but also actively phase out the fossil-based generation. So that all fits together. But we know how to build solar farms. We know how to build wind farms. That's all known. And we know how to mothball fossil generation plant. All known. So then the second area is we have to connect those assets onto the grid. But again, I would argue that's well known. We know how to build out transmission lines, distribution lines, interconnectors. Again, well known and understood technology. We have a playbook for all of those elements in those first two big areas, building and connecting renewables. The third one is the one that we're interested in. That's how do you operate a power system with 100% renewables, because it hasn't been done before. And I liken it, personally, to it's got the same level of challenge and innovation as, I would argue, the actual original inception of an alternating current power system. We will have to re-architect the entire power system to be able to run on very, very different assets that no longer provide the same amount of stability. And I think your analogy is also very, very appropriate, because you've talked about this sort of peer-to-peer mesh network type of approach. That is definitely going to be part of that architecture. But the thing that is missing, in our view, is data. I mentioned earlier that because the power grid has been so stable for so long, that the need to measure has been almost reduced and removed. It's changing now, obviously, but really the measurement in the power grid sort of started and ended within SCADA systems. You just got to report your power generation output if you're a big generator every 15 minutes into the control room of the grid operator. That was it. Because everything else, was stable, the grid was stable, most of the energy was coming from these big generators. So as long as you looked after that side of the grid, everything else would take care of itself. But that's obviously changing. And the bit that's then missing now are these new critical operational parameters that only rise to the surface because the fundamental physics are starting to change. And that's the domain we are trying to operate in. And because of that, we are looking at how we measure the things that haven't been measured before. And part of that is hardware, developing very, very high precision, high gain, high sampling rate measurement devices to find these, very, very obscure, potentially phenomena in the grid. But those are the things that if you catch them early, they're cheaper to fix. You don't run as big a system risk because you know about them early, and you maintain, hopefully the lowest cost operation for consumers. So it's that third bucket, how you actually operate a power grid when the physics have fundamentally changed, that I believe is the challenge that the whole system is starting to get to grips with, in all honesty. And it follows that natural, sequence of events. If you haven't built the renewable assets, it's not a problem. If you've built them but you haven't connected them, it's not a problem. But if you've built them and you've connected them and you've got to run them and you're not allowed to curtail them, it is a problem. And you've got to find a way to solve it. So it really is opening up, I would say, new levels of understanding of how the system actually operates, which is the super exciting thing from our perspective. It's also exciting for our customers, because we can give them visibility of things that they've not seen before. We can show them, so, a power station fails. The way that normally happens is that it's a 2 or 3 week engineering task for a team of 2 or 3 or maybe 4 engineers in a power grid to find out what happened, which of the generators failed on the transmission grid. Wasn't any of those. Okay, so where did it come from? Because, many grids don't have visibility of the distribution network. So they have to go on this sort of, quite detailed investigation to find out what happened, why did it happen, where did it happen, when did it happen. But, if you've got a network of measurement devices that are super, super accurate, super high precision, super granular, we can tell you in a couple of seconds, and we can show it to you as a video, and we can show you where it happened, which was the asset, how did it affect the grid, how did it destabilize the different regions of the grid. And you can see that almost instantly after the event has happened. And we believe it's that kind of real-time, insight-driven data that is really crucially important for managing a power system when you won't have time to solve problems. That's the commodity you don't have anymore, because your physics have changed and you have less and less time to keep the lights on and keep the system secure.
So Mark, earlier you said observed some phenomena, and that's a plural.
Yeah.
Phenomenon, I was thinking, if you would have said that, well, maybe inertia was the big phenomena that you came upon. But what other things are there to measure besides inertia?
Well, yeah, very good question, Jim. I mean, there's a lot. There's a lot. So yes, phenomena in the plural. So you have to start to break it down a bit. So inertia is important for frequency. So really, that's in the preserve of transmission grids, because in the transmission grid, that is where you have the grid operator that is maintaining that system frequency within relatively tight tolerances to make sure that linear flow of power throughout the whole power system is well controlled and contained. So frequency behaves differently based on the amount of inertia. So you go to the heart of the issue and you understand inertia. That tells you how you can understand frequency. That tells you how you can better define the kind of response services that are going to be most effective for your grid. So again, if you think back, 10 years ago, a grid operator might have had a primary response service where they needed a gap between, a power station failing and, diesel backup generation or CCGT switching on, which was about maybe 7 or 8 minutes. So they needed a faster response that could hit the ground running within those first 7 or 8 minutes until such time as the conventional generation could kick in. Fast forward to today, potentially it's sub-second. So you need more batteries. But you've got to be careful. If you have a grid that is so weak that you only have a sub-second type of response, if you have too big a response from batteries, those might push frequency above where your upper band of frequency is, and then those same batteries will look to reduce that frequency back down, and it might undershoot the bottom end of the frequency, and then you're suddenly in a cycling scenario. And again, it's because you have missized the amount of frequency response of a certain type of asset to the physics of your power grid. So you need to understand and have that measurement underpinning your understanding of your power system, so you can better optimize the kind of frequency response services you then buy and contract for. Also, the investments you make. A lot of grids are looking to reinforce their transmission grids and their distribution grids with synchronous condensers. These are very expensive items, $10, $30, $40 million for each one. Again, if you don't know and you haven't got empirical data to help you understand where the weaker and stronger parts of your grid are, you might put them in the stronger parts of your grid and they may be less effective. You may have procured too many or too big. So by understanding this at the first principle level, the physics of your power system, you can optimize your investments much, much better, make them more effective. But then if we look at the distribution grid, we don't care about inertia so much or frequency, but we do care about voltage. And again, as you lose these big synchronous generators, you start to lose the fault-in feed, the nice heavy voltage that goes into the distribution grid that keeps the voltage strong and stable and secure. And you start to see voltage become weaker, which means that, synchronous engines can't actually get into the right phase in the distribution grid. Or you start to see that distribution grids have to curtail renewable energy. They have to disconnect it because they're seeing that their voltage is becoming too weak in certain parts of the grid because there's just now more embedded generation and the demand hasn't increased to match it. So you start to see the whole physics start to change throughout the whole power system. And again, we believe it comes back to measurement. So if you're a distribution grid and you want to have a real-time, DERMS or ADMS system that will optimally provide the right response to reinforce and strengthen your grid, you want real-time data to do that. You don't want a model that is only updated once a year. I attended a conference last week in Anaheim in Los Angeles. It was an IEEE event. And, what came out of that loud and clear is that the models that grid operators have been using for so long have not been able to keep up with the scale and the pace and the complexity of change of all the assets that are going onto the power system. So the models are not able to replicate what is actually happening on the power system. And that's really where we believe measurement data comes in, which can not only drive better operational assets and tools for the grid operators to reinforce and stabilize and secure their grids, but they can also improve the accuracy of those models because then there's a proper feedback loop. So again, we're looking to plug these gaps with hopefully quite, insightful and critical data sets that just haven't existed up until now.
In regard to these models, is it are they simply not granular enough data, or is it a time-based issue, or is it both, or something else?
Well, it's both. It's both, Jim. It's both. Some of it depends on time. Some it simply might just be, that an engineer needs to go to a substation and take some measurements of voltage, but they, how many substations there are in a big distribution grid. I mean, it's hard to just mobilize the people to get out there. So it might just be once or twice a year. So that's just one or two data points, or, maybe it's a few hours, but it's one or two times a year. And are those really the most extreme scenarios to cater for? So that's why models become conservative, but also models have to be based on, almost historical experience. And we are seeing things that have not been done before. As I said, running a power system on 100% renewables has not been done before. The only countries that are running very high renewables are either heavily interconnected within larger grids, so they're insulated from other grids that have got high amounts of inertia on them, or they have effectively renewable baseload. They have geothermal or hydro in large quantities.
Yeah.
When you talk about running a power grid purely on solar and wind, no, there is no playbook to do that. There's the tools, and we believe, those tools can be applied to get there. But in terms of having an empirical, long-standing data set that can, be used to create a tool or a model that can really help, that is not a given at all. And so I think the tools are not capturing the kind of problems that the grids are now seeing. And that's why measurement is important, to create that feedback loop into those tools, so those tools become better and more accurate. So it's got to be part of an iterative process, that the measurement data underpins the tools, that underpins the planning, that helps the operational decision making.
So, Marc, we've covered a lot of ground today. What recommendations do you have for grid operators for today and then moving into the future?
Well, I don't know if I'm really qualified to make recommendations to. I think you've set me up there, Jim. But I would say, well, let me give you the case study of the UK. So we've run this service or this system now for National Grid for it's approaching 2 years. We made now we have a decent data set, so they've been able to see based on our measurement data. I said, we're measuring more capacity of inertia than they would typically estimate. What that data shows is that we're saving on an annual basis 18 million tons of CO2 a year, because they are no longer curtailing as much renewables as they were before, and they're no longer having to use as much fossil generation as before. So 18 million tons a year is about 5.5% of total UK annual CO2 emissions, which is, I think that is nationally significant. And it was on the back of that case study that, we were very hugely honoured to be given a COP 28 Energy Transition Changemaker Award, because we can see now, and National Grid can now see, that they need this real-time data to help them navigate this technically challenging course through to using more and more renewables on their power system, but keeping the same levels of system security, the same levels of safety, and hopefully also enabling more effectively cost reduction measures to filter through, so consumers have lower costs at the end of this, and yet a cleaner and greener power system. So I would say measurement is critical. It's not to say that models don't have a role. Of course they do, but really now models need that real-time feedback to improve and keep them at the forefront of planning decisions. But more and more, we think in an operational context, grids need a new dashboard. They need to look through the front windscreen, and they need new dials to tell them how the power system is actually behaving at that moment in time, that can also give them visibility like forecasting to say in 4 or 5 or 24 hours you're going to need X, Y, and Z. And that data is now starting to become available. And the grid operators that are starting to use it are realizing that they can't see a way forward without using that data. So hopefully that those would be the kind of collegiate recommendations, because we don't want to tell anyone how to run their power grid. We don't have that huge responsibility, but as a company, our mission is to enable the net zero or the renewable energy transition to happen. So we want to ensure that we can provide the tools to enable grid operators to do the best possible job they can, which is an incredibly challenging task. Make no mistake.
So Marc, as we wrap up today, what final thoughts or messages would you like to share with our audience about Reactive Technologies and your vision?
Well, I would say it's a privilege to work in the industry. I enjoyed semiconductors, but I think for me the power industry is like the eye of the needle. So when you look at what it will take to decarbonize the world, let's say, every key decarbonization thread has to flow through the power grid. If you're decarbonizing transport, if you're decarbonizing manufacturing, if you're decarbonizing heating, all of those decarbonization initiatives ultimately have to start and end with the power grid. And so it feels genuinely like we can help and we can contribute something positively. As I said before, we're a mission-led business. For us, this is everything that we do. We are hugely excited to be working in the States. Again, a few weeks ago, we were able to announce that we will be measuring inertia for the state of New York with the New York ISO. working with NYSERDA and 5 other leading utilities in the New York State region. So we just can see that we can help, and because the physics is the same in any power grid, the tools and the capabilities that we can bring to grid operators are going to be very, very beneficial for them. So we want to do more in the US, but also more and more worldwide. So, I think it's a phenomenal industry. And when I joined it in 2010, I remember that's the moment when apparently the smart grid was just about to happen. And I think 14 years in, we can say, yes, the smart grid is genuinely about to happen, and it genuinely feels like it. So I would say the next, 10 plus years are going to be a really, really exciting ride, and hopefully a very positive one.
Well, Marc, lastly, if some of our audience would like to contact you, can you share some of your contact information?
Well, that would be very kind of you, Jim. Yes, we have a website. It's a long one, unfortunately. It's obviously www.reactive, and then a hyphen or a dash, technologies, which is plural, and then .com at the end. Or look me up on LinkedIn, or the company on LinkedIn, and we have our email address, info@reactive-technologies.com, and we would love to hear from people for sure. And there are some on the website. We've got some white papers. If my discussion today with you wasn't geeky enough, there's even more technical gems on the website that people might want to look into to understand inertia in more detail. So we're here to help for sure.
Well, thank you, Marc. Again, to our audience, today we've had a fascinating hour with Marc Borrett, CEO and founder of Reactive Technologies. Marc, hopefully we'll have you back in the future, and thank you again for joining us. And to our audience, we'll see you again on another episode of the Sustainability Podcast very soon.
Thank you, Jim.